Hello, everyone. Today we continue with looking at some of the problems of homework. So I would start by just reviewing the previous homework you had. We would take a look at that very fast. And then we also would look at the homework you're supposed to hand in. Of course, I'm not going to solve that. I'm just going to mention a few things. And then if you have time, we would solve some more problems. Okay. Is there any question before I start? Okay, if no, let's start. So this week, the homework which you handed in, not the one you should hand in today, the previous one. I want to just take a look at that very fast because there were some common mistakes in your solutions. So question number one was about T and operator, or a linear map, actually, between finite dimensional vector spaces. Well, here both of them are the same, a vector space V. And we wanted to show the followings are equivalent. The followings are equivalent. A says V is equal to null of T plus, or kernel of T, which is, I think, more common, plus range of T, or image of T. Part B says V is equal to null of T, direct sum range of T. Part C says null of T, intersection range of T is 0. Part D says null of T squared equals null of T. And finally, part E says range of T squared equals range of T. Before starting to solve this one or talk about this one, does anyone have any example in mind? Let's first find a few examples. Can you come up with an example for a vector space V and a linear map T which satisfies one of these properties, and equivalently it would satisfy all of these properties? So if you have an example in mind, you can unmute yourself and you can just share it with others.
The identity.
Would you say again?
The identity.
The identity, yeah, that's one example. So let's take V to be some vector space, doesn't matter what, and let's take to be the identity map from V to itself. So it satisfies these properties. We can see that. So because the null of T or kernel of T would be the kernel of identity, but for identity map, the only thing which projects into 0 is 0 itself. And the range of the identity map is, of course, all of V. So, and it's easy to see all of these properties, they hold here, right? But now let's take a little bit more non-trivial example. So that's correct. That's a first example. Let's present a second example where the map is not identity. And let's choose something. So let's try to find a map where, unlike the previous one, the null of T or the kernel of T is not just 0. Let's find a map which its kernel is something non-trivial.
All right. How about the map in which the kernel is the entire space itself, for all V and V, TV equals the 0 vector?
That is correct. So the second example we can think about is V can be anything. T can be a map from V to itself, where T of any vector U is 0. So it sends everything to 0. So now null of this map T is everything and the range of this map T is 0. Again, as you can see, they add up to the whole space V. Well, now the third example, of course, we want to make it more non-trivial. And as you can guess, now we would like to find a map T which its kernel is non-zero. So it has a non-trivial kernel. Also, the range is non-zero.
If you take V equal to R squared or R2, could you use the map X comma Y maps to X comma 0?
That's great. Yeah, projection map. So this is a very good example, actually, because it gives us an idea about the more general case. So suppose we have a map T from R2 to R2, where T of X and Y is equal to X and 0. So this map simply, although the domain and codomain both are R2, but in some sense, the range is only the x-axis. So what happens is that for any points x and y, this map would project that point to its projection on the x-axis. That's what it does. So kind of the whole space R2, it collapses and we would just get a line, right? So what is the kernel of this map, or the null space of this map? There are different names for the same thing here in this course. What is that? So that is equal to every element in R2 in the domain such that T of that is equal to 0. But 0 of this vector space, right? 0 and 0. On the other hand, T of x and y is equal to x and 0. And x and 0, therefore x and 0 should be equal to 0 and 0. And the equality should hold component-wise, and it means x is equal to 0. As you can see, there is no restriction on y. Y can be anything. And it's also kind of clear in the image we have on the left-hand side, because this is 0, right? This is the point 0 and 0. And nullity of null of T, null space of T, or kernel of T, is the space which would project into that point 0. And obviously, this is the subspace of R2, which goes to 0. So that's null of T, as you can see. These are the points of the form 0 and y for any y, which is exactly what we got here. So it would be 0 and y, where y is inside R. So this red line here is null of T. What is the image of T? Well, or the range of T. Both of these things are they're equivalent words for the same concept. The range of T is T of all R2, which means T of all points x and y, where x and y is a point in R2. And that is equal to x and 0 for x in R, right? The image of x and y is x and 0. And that's this other axis. So that's the range of T. Now, as you can see, the range of T and null of T here, their sum would span or would construct or would give us all the space R2. So anything in R2 can be written, anything in R2 is an x and y, and it can be written as sum of two vectors, one in the blue subspace, one in the red subspace, right? So that is correct here. Null of T here, which is the blue subspace, plus the range, null of T is the red subspace, the range of T is the blue one. Their sum gives us the whole space, because any x and y can be written as sum of x and 0, which is a point here, and 0 and y, which is a point in the null space. So it's another example. So in general, projections, they give us these kind of maps. That's one of the examples. So if you project, if you have a vector space and you take a subspace, if you project into that subspace, that would be an example of maps satisfying these properties. That's one point. It's good to know a few examples of something before proving statements about them. Sometimes it's very illustrative. The other thing I want to say is that when we are proving these kind of statements, that we have a few statements and we want to show they're equivalent, usually there is a kind of efficient way to do that. So in a lot of solutions I was looking at, your homework, what you have done is that you have proven A implies B and B implies A. B implies C, C implies B, C implies D, D implies A, D implies E, and E implies D. And a lot of other things. For example, you have shown E implies B, B implies D, and vice versa, and a lot of them. You don't need to do that. So it's a very good thing to do as an exercise. That's great. I mean, that's what we want to do. But just in order to know that as a fact, when we have these statements, we want to show they're equal, A, B, C, D, and E. For example, if we show A implies B, B implies C, C implies D, D implies E, and E implies A, that proves that these are equivalent, because it proves everything else, because it shows C also is implying B. How is that? Well, it shows C implies D, D itself implies E, E implies A, and A implies B. Therefore, C implies B. I don't need to write another proof that C implies B directly, although I can do that. And as I said, that's a good exercise. Sometimes you might not find, I mean, the way the question is presented, maybe it's not in the most straightforward way. Maybe I could shuffle these statements, A, B, C, D, and maybe it wasn't the best idea or the easiest way to prove this equivalence wasn't exactly to go through these arrows. Maybe it would have been easier to, for example, here, one might find it easier to prove it the other way. For example, B implies A, that's more trivial, right? And then maybe someone wants to continue this path and shows A implies E, and then E implies D. And you don't even need to go in this order. You might find a more strange order that would work better for that question. So let's just have that in mind too. Okay. I'm not gonna give you, so is there any question about how we can solve this problem, about any? So I think for this question, really the best way was to really go through this order. A implies B, B implies C, C implies D, D implies E, and E implies A. So if you have any question about any of these implications, you can ask now. If any of them is confusing to you or you couldn't solve any of them, you can say that. So just take a look to make sure. If you couldn't do one of them or two of them, I can solve it now.
Could you please do the D implies E proof?
Yeah, sure. So yeah, that's great. So D implies E. Let's see. We want to show if null of t squared is equal to null of t, then range of t squared is equal to range of t. So what we know is that we have a linear map t from V to V. We know null of t squared is equal to null of t. And we like to prove that range of t squared is equal to range of t, right? That's the question. So so first note that these are subsets, right? Range of t squared, there are sub-vector spaces or vector subspaces. And therefore there are sets. And whenever I want to prove two sets are equal, I want to show each of them is the subset of the other one. So in order to prove this equality, I would like to show two things. One is that range of t squared is a subset of range of t, right? That's the first one. The second one is the opposite case, that the range of t is a subset of range of t squared. Okay, so one of them is fairly simple and kind of trivial, and that's number one. Any element in the range of t squared is an element of range of t. So when I want to show one set is a subset of another set, I should show any element in the first set is also an element in the second set. So if I want to show this inclusion, that range of t squared is inside range of t, I should show for any element, say u, inside range of t squared, it is also an element of range of t. Right, that's what it means to be subset of another set. Now, if u is so this is my assumption, and this is what I want to prove. So let's look at our assumption. If u is in range of t squared, it means u is equal to t squared of something, right? So let's show that with w. And look at the right-hand side. I want to show u is in the range of t. It means u is t of something. And that's correct, because if u is equal to t squared of w, it means u is equal to t of w. Now, if I change the name of this t of w to something else, say, let's call it z, it means u is equal to t of z, right? So we can see here that u is t of something. So u is in the image or in the range of t, which is this thing. So that's the first part. The second part, which is slightly more involved, and now we should use the assumption we had. Remember, we still have not used the assumption that null of t squared is equal to null of t. So now I want to show range of t is also subset of range of t squared, right? Now, what can I do now? How can I show this other inclusion? There are two ways. One is the direct way. The direct way means I can take an element inside range of t, and then I can try to show it is inside the range of t squared. It is t squared of something. We can do that. That's not hard. We can do that. But also there is a slightly different way. And rather than proving this one, so the indirect way is, rather than proving this one, is this other thing. So suppose I have a vector space V. Well, we have V. Let's say we have vector space W and a vector subspace U inside that. So here, for example, this is the range of t squared, and this is the range of t. We proved that the range of t squared is a subset of range of t. And also, suppose we know these are vector subspaces, which that's the case in our case. So there is a concept of dimension. They are finite dimensional. suppose also we know their dimensions are equal. So one of them is a subspace of the other one, but they have the same dimension. That implies these two have to be equal. Okay, so if one of them is inside the other one, but they have the same dimension, they are equal. Now that's what I like to do now. Okay, so remember, when we have a map T from V to V, we know dimension of V is equal to dimension of null of T plus dimension of range of T, right? But on the other hand, T squared itself is a linear map from V to V, right? Combination of linear maps is another linear map. So I can write down this theorem for any linear map, including T squared. So dimension of V is equal to dimension of null of T squared plus dimension of range of T squared. Now here we should use our assumption. The assumption told us null of T is equal to null of T squared. So their dimensions should be equal, right? On the other hand, on the left-hand side, dimension of V, of course, is equal to dimension of V. What does that tell us? So if dimension of V is equal to dimension of V and dimension of null of T is equal to dimension of null of T squared, the remaining parts of the equations should also be equal. So dimension of range of T is equal to dimension of range of T squared. So we have two spaces, one of them subspace of the other one, but they have the same dimension. So they have to be equal. So it means range of T is equal to range of T squared.
How do we know that the dimension of the null space of T is equal to the dimension of the null space of T squared?
Well, that was the assumption. We started from part D and we were going towards E. And the assumption of part D is that null of T squared is equal to null of T. So if they are equal, if two spaces are equal, of course, their dimensions is also equal to. So this was the assumption that these two spaces are equal.
That I understand, thanks.
Yeah, great. Okay. So that was the first question in the homework, and the second question was, well, I would just write down the second question. The second question was slightly similar. Again, we have a linear map from V to itself. V is a vector field, sorry, it's a vector space over field F, which its characteristic is not equal to 2. So characteristic of F is not equal to 2. And we know T squared is equal to identity. That's part of information we have. Now we want to show the space V can be written as null of T plus identity plus maybe, yeah, and T minus identity. Sorry, null of T minus identity. So also for this question, I want to show, so I have a vector space, I have a linear map. If T is a linear map, T plus identity is another linear map, and T minus identity is another linear map. So their null spaces, or their kernel, they are subspaces of V. And here I want to say I can write down this space as their sum. Okay. So I would just write down the answer to this one very fast. It's not hard to see. Well, any map, any vector V can be written as 1/2 times T of V plus 1/2 T of V minus v. The reason I can write 1 over 2 is that the characteristic of the field is not 2. So if the characteristic of field is not 2, you know any field has this element 1. And I can define 2 to be 1 plus 1. Oh, no, it's fine. I would, oh, you're right. Yeah, sorry. It would be minus TV plus v. So I have 1 plus 1, which that is 2. And because the characteristic is not 0, this is a non-zero element. If 1 plus 1 is equal to 0, then the characteristic of the field would be 2. So this is a non-zero element. And any non-zero element has multiplicative inverse. There is an element which is multiplicative inverse of 2. I show that with 1 over 2, just because we're used to writing it like that. So of course, you can see the right-hand side. The sum is equal to v. And so now, why are these in the kernel of these spaces or not? So I can, maybe it would be nicer if I write it as v minus tv and tv plus v. So how does it help? What would you get if you apply t plus identity to these vectors? So let's try. For example, let's see what would happen if I apply t plus identity to this vector v minus tv. Well, I would get tv minus t squared v plus identity of v, which is just v, minus identity of tv, which is just minus tv. Okay. Now, on the other hand, t squared is identity. So t squared is just identity. Therefore, t squared of v is just v. Now you can see tv would cancel with minus tv. And here we have a minus sign. So we have minus v, which would cancel with plus v. And the result is 0. So this vector here is inside this space. And in a completely similar way, this other vector is inside this other space. This is the first part. It shows me any vector inside this vector space V can be written as sum of two vectors, which one of them is inside this space and the other one is inside the other space. Now I want to show this is a direct sum, right? From the previous question, we know in order to show this is a direct sum, well, I mean, from the definition, actually, we need to show, or we can show their intersection is 0. So I like to show null of t plus identity, intersection of null of t minus identity is just 0. Well, suppose it is not, or we can just prove it directly. Let's take an element v there. Let's take a generic or arbitrary element in the intersection. Because it's in the intersection, it's in the first space, and also it is in the second space. Well, if it's in the null of t plus identity, means t of v plus identity of v, which is just v is equal to 0. And if it's in the second space, it means t of v minus v is equal to 0. So if these two are equal, if we subtract them, we still would get 0. So t of v plus v minus t of v minus v would be 0. But this subtraction, this difference, the result here is 2v is equal to 0. Again, because the characteristic of the field is not equal to 2, 2 is invertible there. So that's kind of interesting, because characteristic of f is not equal to 0. I can multiply both sides by inverse of 2. Now the left-hand side is just v, the right-hand side is 0. So any v here in the intersection is equal to 0. Therefore, the intersection is 0. So again, we are using the fact that the characteristic is not equal to 2. And for the last part, so some of you have proven the last part directly, and unfortunately, you didn't get the complete score for that part. The point is that the last part, part B, says deduce from part A. So you can prove it directly, but the question is asking you to use part A. So the last part says show any real valued function can be written as sum of an even function and an odd function. So yeah, you can just say for any f, the function f of x is equal to f of x plus f of minus x over 2 plus f of x minus f of minus x over 2, right? If you just add them, they would cancel each other. The first part is even and the second part is odd. But the problem here, in that solution, we have not used part A. If we want to use part A, we should first define a vector space V, and then define a linear map T, and then use the theorem we proved. So what is the vector space V here? What should be the vector space V? Can you tell me?
Space of all functions R to R. That
is correct. So exactly, the set of functions from R to R. And what would be the linear map T?
T of f of x equals f of negative x.
That is correct. T of f of x, we can define it to be f of minus x. So the simple thing here is that t squared of f of x is equal to t of f of minus x, which is equal to f of minus x, which is f of x. So t squared is identity. And now the previous question, the previous theorem tells us the vector space V can be written as null of t plus identity plus direct sum t minus identity. Now V here is the set of functions like f, right? What is null of t plus identity? It means t of f of x plus identity of f, which is just f of x, is equal to 0. It says that. But on the other hand, t of f is f of minus x plus f of x is equal to 0. That equation tells us f of x is equal to f of minus x. Maybe I should have used another notation. I'm sorry. Let's write g rather than f because we have used f for a different function. So anything here in this null space is equal to, it's an odd function. So the set of all functions from R to R is equal to the set of odd functions plus, and then nullity of this space becomes the even functions. So it doesn't give us the exact presentation, just this is a statement. It just tells us this all functions can be written in this way.